Re-ranking every query is expensive, and skipping it hurts quality on the hardest searches. Query performance prediction lets you spend latency only where it buys better results. This is the pattern you'll be able to implement by the end, which assesses query difficulty and conditionally re-ranks results to cut unnecessary latency. I'm Professor Pi, teaching search and IR with simple Python. Search systems face two costs at once. You want high accuracy. You also want low latency. Re-rankers give big quality gains, but they are slow. Query performance prediction helps decide which queries actually need that extra work. It is a small, fast model that flags hard queries, so the system re-ranks only when it likely improves top results. Intuitively, easy queries show a clear leader among candidates. Hard queries have many near ties, so a simple gap or a tiny classifier can predict when a re-ranker will help. That prediction is cheap compared to running the re-ranker on every request. We will build a tiny pipeline that first measures simple signals from initial scores, then trains a small model to predict failures, then uses a probability threshold to limit re-ranking to a budgeted fraction of queries. This keeps latency low while recovering most of the quality gains before we apply the re-ranker. Now we start by measuring score gaps to get a feel for query separability. This snippet estimates query difficulty from the gap between the top two retrieval scores. The dictionary tops holds 3 example queries with 3 descending scores each, standing in for a small candidate set. The variable gaps computes a per-query margin by subtracting the second score from the first, a simple signal that larger margins imply easier queries. The variable AVG gap averages those margins across all queries for a quick overall difficulty indicator. If you expand tops with noisier scores, the average will shrink and hint that more queries are ambiguous. The printed average score gap conveys how separable top results are and why many queries may not need re-ranking. Next, we create a tiny synthetic dataset that mimics easy and hard queries. This example builds a tiny synthetic dataset of query-level features and labels, indicating whether the initial ranker hits at the top. The list X collects 3 intuitive features per query: the top score, the gap to second place, and the mean of the top 3 scores. The list Y stores a binary label where higher gaps make hits more likely, using the variable P as a probability of success. This produces a realistic mix of easy and hard queries, while remaining deterministic via the fixed seed. Raising randomness without changing the seed broadens difficulty variety. The printed baseline miss rate shows how often the initial ranking fails before any prediction or re-ranking logic is applied. Now we train a simple classifier to predict which queries will miss at the top. This code trains a LightGBM classifier to predict whether a query will miss at the top and likely benefit from re-ranking. The split uses the first 70% of the synthesized examples for training and the rest for testing. The object clyth is a LightGBM LGBM classifier with a fixed number of trees and seed for stability, and fit learns from features in TRX and labels in TRY. The method predictProba returns probabilities for the positive class on TEX, and a 0.5 threshold yields a quick accuracy check. Increasing N estimators usually improves accuracy at the cost of more CPU. The printed test accuracy reflects how well the model separates easy and hard queries. Next, we turn probabilities into a re-ranking policy that respects a latency budget. This snippet converts LightGBM probabilities into a practical re-ranking policy by matching a desired re-rank rate. The variable target states the fraction of queries you can afford to re-rank under a latency budget. Sorting probs from the LightGBM model and indexing by K finds a threshold THR so that roughly the top target share trigger re-ranking. The variable rate then measures the actual share to verify the policy, which can differ slightly due to ties. Raising target increases recall headroom, but costs latency. Lowering it saves time, but risks missed fixes. The printed actual rate confirms how closely the threshold meets your re-rank budget. Finally, we simulate the trade-off between quality improvement and extra latency. This example simulates how the thresholded policy affects the quality and latency on the test queries. The list miss0 flips the ground truth to a miss indicator, and do RR flags queries above the chosen threshold THR for re-ranking. The list miss1 applies a simple fix rate fix P to reduce misses only where re-ranking happens, while lat adds RRMS to the base latency when re-ranking is chosen. Tuning fix P reflects re-ranker strength. Tuning RRMS reflects its computational cost. Larger fix P reduces misses, but only where do RR is true. The printed miss after and average latency summarize the resulting trade-off and show whether the policy meets your practical goals. In a real system, this maps cleanly. The initial ranker is your fast retrieval step. The classifier runs in milliseconds, and the re-ranker is the heavier model you call conditionally. With a few thousand queries in validation, you can set a re-rank budget and tune the classifier to maximize saved latency while minimizing missed fixes. Recap. First, query performance prediction estimates which queries need expensive re-ranking. Second, use it when re-rankers are costly and latency matters. Third, watch out for false negatives. Missing a hard query keeps the user unhappy. Wrap punch. One practical next step is to tune the re-rank budget and model strength together. Increase the re-rank fraction or increase classifier complexity and measure how many misses you recover per additional millisecond. That trade-off is the whole point. If short practical IR helps, subscribe and watch the IR videos.